Well, this is Chapter 5-5, Indirect Proofs, which is using indirect reasoning, and sometimes this is called proof by contradiction. So the way you go about doing this is you start out, like any proof, you just identify what it is that you're trying to prove. And what's different in this type of method of doing proofs is that then you take what you're trying to prove and you negate that. You write the negation of that conclusion, and then you use it in your proof as a given, and then you logically move forward with your proof until you reach an impasse, a contradiction. And so therefore, if you reach that contradiction, then what you assumed, the negation of the conclusion, must be false. So therefore, your original conclusion has to be true. So let's start out with a simple example. So let's try to prove that person A is awesome. Isn't that the most greatest picture of that person and address there? So you start out identifying that A is awesome is what we're trying to prove, and then you write the negation of that. You write A is not awesome. And then I'm throwing in some arbitrary givens that just to get this proof to go forward there. So we'll say that A has a great personality and that A works hard and helps others. So since those two statements are contradictory to this statement 1, that she is not awesome, then therefore that statement is false, therefore A is awesome. So this is proof by contradiction. Let's see if we got a geometry example for us. Oh, I forgot. We had to say this. Since we came to the end conclusion that A is not awesome is not true, that's really in effect saying that A is not awesome. So the nots cancel out, so A is awesome is another way of looking at this. Okay. Geometry proof. So if we have ABC can have at most only one angle that's equal to or greater than 90 degrees. That's what I want to prove. And so I rewrote this numerically here, that I'm picking just one angle, angle A, that is equal to or larger than 90 degrees, and the other two angles have to be less than 90, and any angle has to be bigger than 0. Okay, so I wrote that out, and then I already discussed this, that all angles have to have a measure greater than 0. And then we also know that the interior angles of a triangle sum to 180 degrees. So I wrote that numerically there. So let's start with our proof. The first thing is we're going to take our original conclusion here, right there, and then you negate it. So I'm going to say here that either two angles are equal to or larger than 90, or all three of them are equal to or larger than 90. Well, if we take the first example here to the left, that two of them are equal in measure or larger than 90 degrees, then that covers the right side. That we just need more than one according to this statement right here. Look, ABC can only have at most one angle that measures equal or greater than 90 degrees. So this left part takes care of it. So let's move forward. So right there we go. We got our two angles that are equal to in measure or greater than 90. Then I'm saying that angle C is in between 0 and 90 degrees. And now, if I'm setting up that the measure of angle A plus the measure of angle B plus the measure of angle C is equal to 180 degrees, and then I'm substituting in these 90s. Why am I picking 90 and not 100? I'm trying to, obviously, if we put in hundreds in there, it's still going to reach, well, it's going to create a negative answer. In either case, we're going to have we're going to have a contradiction, so I just went with the minimum number. So we got 90 plus 90, okay, we got 180 there, and then I've subtracted 180 from both sides, so therefore the measure of angle C is equal to 0. Well, it can't equal 0 or be less than 0, so therefore both a measure of angle A and measure of angle B cannot be both either greater or equal to 90 degrees. So this statement here, our temporary assumption in the very beginning there at line 1, must be false. Therefore, only one angle can be equal or greater than 90 degrees in measure. Okay, let's do one last one. So this proof, we're going to take the given is that ABC, which I drew down in here, triangle ABC, is scalene, meaning that the sides are all of different measures. And then you're given that BD bisects angle ABC. So BD right there is bisecting ABC. So I wrote, oops, that wasn't the one I meant to move. Oh, and then what we're trying to prove. We're trying to prove that BD is not perpendicular to AC. Well, using proof by contradiction, indirect proof, we're going to assume the opposite of this. So BD is perpendicular to AC as an assumption. So here we go. There's the first given. And then while we're there, I'm quickly establishing that, look, if BD bisects ABC, well then this angle here, ABD, has got to be equal in measure or congruent to angle CBD. So I wrote that right there. And then I'm going to do my temporary assumption that BD is perpendicular to AC. Well, if they're perpendicular, then they form right angles, so that's what's taking place here. And then, oh, I should write that in the picture. So let's see. So look, there's my little right angles. Yay. There's another one. Yay. Okay. And then, well, if they're both right angles, then they have to be of equal measure. So they're both congruent to each other. And now we got BD is congruent to itself. So there you go. I put a little tick mark there to take care of that. So that's reflexive property. And now let's move this down a little bit. See, now we've got this triangle to the left, ADB, is congruent to this one to the right, CDB, because of angle side angle. And then we can say that, let's get some color here. So we can say that that side is congruent to that side by CPCTC. Okay? And then, well then, let's move this yellow mark down a little bit. There you go. Then triangle ABC has to be isosceles because this side is congruent to that side. Well, it can't be isosceles because we started out by saying that ABC was scalene. Therefore, we reached a contradiction. So, right here, let's try to circle it, or I'll just highlight it. Oh, there we go, underneath. BD is not perpendicular to AC. Right there. That's what we're trying to prove. And that's it. Thank you for watching this video.